So, all right, let's get started. So currently we are discussing about data streams. And the last time we have discussed about a couple of examples. For instance, if you have a stock ticker stream or if you have sensor data that keeps being generated, then often you want to model this as data stream. And there is specialized systems for processing those streams. The last time we have started discussing about one of those systems. It's already one of the more classical ones from Stanford. This system has several interesting features. One of them is how it tries to minimize the amount of data that it has to store in the system, because those data streams, they are essentially unbounded. So it is very important to throw away data when we don't need it anymore. Now, we have discussed about a couple of ways in which the system tries to minimize the amount of data to store. For instance, if you have multiple operators in the system and they have to store tuples, sometimes they have to store the same tuple, so you want to overlap that. This is what I mean by synopsis sharing. Also, we have seen that there is constraints, for instance, on when certain tuples can arrive in certain streams. And if we exploit those constraints, then we can also often reduce the amount of data that we need to keep around. And then finally, I've mentioned that we can also shrink intermediate results by smart scheduling. And in the following, we're going to see a little bit more how that works. So we are going to discuss about scheduling policies. And as a little reminder, so in this stream data management system, the different operators in a query plane communicate via queues. Each operator has an input queue and an output queue. And in those queues, you have information about what changed in the data, about the tuples that were inserted and about the tuples that were deleted somewhere. And since I have those queues between the different operators, I have a little bit of freedom about when I invoke a certain operators in order to process their input queue or part of their input queue. And there's multiple different scheduling strategies. The simplest one is the FIFO, first in, first out policy. Here, essentially, whenever we have one new input batch in the system, then we will process those tuples completely before we look at the next input. So here, if your operators form a chain and you have a new batch of tuples arriving at the beginning of that chain, then you will consecutively call all the operators in that chain in order to completely process the input tuples. That's one possibility. There's also the greedy policy, which essentially means that we don't necessarily call operators in a fixed order, but instead of that, we will always call the operator that can probably get rid of most tuples in the system. So here we greedily try to get rid of tuples as quickly as possible. And then they also propose some mixed strategies. For instance, you can group your operators in the system and then use a greedy strategy in order to decide which group to invoke next. But within the operators in the same group, we use the simpler FIFO strategy. So there's a couple of ways of mixing that. In the following, I'm going to illustrate the differences between FIFO and greedy scheduling by a little example. So here we have a chain of two operators only. We essentially get the input, then operator 1 seems to be a filtering operator. It has a selectivity of 20%, which means that for each input batch of tuples, approximately 20% of them pass the filter. And then we have a second operator. The precise type of that operator does not matter. In each case, I have two queues in the system that I care about. That's the input queue, input to the first operator, and this intermediate result Q, which is the output of the first operator and the input to the second operator. I don't care anymore about the final output of the system because that doesn't have to be stored in the system. Perhaps it is directly forwarded to the user or to a different system. So I care mostly about minimizing the sizes of the input and of the intermediate result queue. Now at the beginning, those queues are empty, and now the following, I assume that we have one new tuple batch in each time step arriving in this input queue. Now in the following, I'm going to illustrate a FIFO scheduling first. So let's assume that the first batch of tuples arrives in the input queue. And since we do first in, first out scheduling, it means that we have to invoke the first operator next. So this is why it is marked in red. And after we invoke that operator, about 20% of the input tuples will remain and be inserted into the intermediate result queue. At the same time, one new batch of input tuples arrives. This is why the input queue does not become empty, but fills up immediately again. So here I assume that we have one fresh input tuple batch in each time step. In the table below, you see that I'm inserting the total size of all queues combined in the system, which now is 1.2 in time step number 1. So here in the next step, I would invoke operator 2 because it's the simple FIFO scheduling strategy. And the result of that is that, first of all, we are getting rid of the intermediate results. On the other side, we have this current input batch in the first queue, and one more batch will be added in the next timestamp. So this is how the queue sizes evolve. And now, as you see, we already have a combined queue size of 2 in the entire system. So now we have completely processed the initial input batch. So now we're gonna invoke the first operator again to process one more batch of tuples, which produces intermediate results of 0.2 batches. And it eliminates one of the 2 input batches, but in the next timestamp, we will get one more input batch. So this is why the input queue size does not decrease. So this is what happens here. And in total, now we have a combined size of 2.2. So as you see, the total number of tuples in the system keeps growing relatively quickly. And now if I continue, I would first invoke the second operator again, which removes the tuples from the intermediate result queue, but at the same time, we allow that the input queue fills up further. So here, now we have already 3 batches of tuples stored in the entire system. And as you can imagine, that continues. So here I'm fast forwarding and filling in the last 2 fields in the table below. And yes, so here every 2 timestamps, we increase the total number of batches stored by 1. Now, let's see whether we can do better with greedy scheduling. So the same situation as before, I assume the same arrival rate, just that now I vary the order in which I invoke certain operators. So now here, one input batch arrives again. And the goal of greedy scheduling is that I always invoke the operator which can reduce the number of tuples the most. So here that is clearly operator 1. So I again select this one, and the result is the same as before. I have a 0.2 batches in the intermediate result, and I have eliminated one input batch, but a new input batch got immediately sent. So now I again have one batch in my input queue. And now the FIFO strategy would invoke operator number 2, but in the greedy case here, we will see that by invoking operator 2 here, we would only get rid of 0.2 batches. That's the content of the intermediate result queue. While by invoking operator 1, we will actually get rid of one entire batch. So that is clearly more desirable. So with greedy scheduling, I'm invoking operator 1 again. And after that, the intermediate result will grow by 0.2. And the input, current input batch will vanish, but a new one will get inserted immediately. So I remain at 1, and the intermediate result slightly grows to 0.4. So in total, I have 1.4 batches stored in the system. And if you compare in the table at the same point in time with the FIFO strategy, now we would already be significantly above that. And if we continue here, now it's the same thing. Operator 1 allows us to get rid of more tuples. So this is why I would prefer invoking this operator in the next time step. And now the intermediate result grows by 0.2 again. And the input doesn't change because one gets deleted, one gets inserted, nothing changes. So now in total, we're at 1.6. And again, this is a lower number of batches than I had stored with the FIFO strategy. So here, selecting greedily pays off. And if I continue this and fast forward and fill in the remaining fields in the table below, then you see this development. I keep increasing the number of tuples by 0.2. So this little example shows already that the scheduling policy can make a difference, and in the system, they exploit that fact. There's a couple of other methods that they use in order to reduce the number of tuples that you need to keep around. Now, the previous strategies, they don't essentially lose anything, so you always want to apply them. Now, there's also a couple of strategies which do lose precision, or they do lose tuples, but if you otherwise run out of memory, then you cannot do anything else. So they consider in general load shedding, which means that we don't process a certain tuples in order to save overheads. And if you have, for instance, a query in the system that calculates aggregates, then even if you don't process some of the input tuples, at least you can still get some kind of sample for the aggregate input, and you can calculate things like confidence bounds, for instance. So you can estimate what would be the aggregation value. For instance, if you calculate an average over some input stream, and then we are dropping half of the input stream, you can still get a pretty reasonable estimate for what the average is gonna be. And if you have multiple queries in your system, then they try to balance out the impact between multiple queries and make sure that no query suffers too much. And in general, those operators, they often have a so-called synopsis. If you remember, for instance, for the join operator, the synopsis would correspond to a hash table pretty much, which allows you to quickly find the joining tuples in the second input if a new tuple arrives for the first input stream, for instance. If we reduce the synopsis size, then we save a little bit more, then we save memory for the current operator. And in many cases, like for joins, for instance, reducing the synopsis size means that less results get generated. So implicitly, we also might save for the following operators, because now they have to process less data. There's a couple of exceptions to that. Can maybe anyone think of an exception? So when can it happen that by reducing the synopsis size, I might actually increase the amount of data that needs to be processed by following operators? If you have a suggestion, please put it into the chat. Let's see the first message. how could it reduce the output size? Okay, great question. So, I mean, for instance, we have a join operator, and the synopsis is one of the hash tables. So if one tuple arrives in the first input, then I use this hash table in order to quickly find the matching tuples in the second input. And now I eliminate, now I just forget half of that hash table, which means that for each tuple arriving on the first input, I will now find less matching tuples in the second table. And because of that, the size of my output is decreased. We can also have another look at the join operator, or does it make sense like this? Okay, awesome. Maybe I anyway show quickly again the join operator that we have quickly discussed the last time. So this is the join algorithm here. This is the graphical representation of the join algorithm. You see that here on the bottom of the slide, we have a synopsis, which essentially corresponds to hash tables for the two inputs using the join column as hash key. So here we assume a join with an equality join condition, and the algorithm works as it is described here. So whenever a tuple gets added or deleted in the first input queue, we extract the join key from the added tuple. Then we probe the hash table, the synopsis that is associated with the other input using the key. And for the matching tuples, we add them to our join result and also potentially update the synopsis. And here, if my hash table is smaller, it will find less matches, so it will generate less output. And now the question is, if we do that, then in many cases, like for joins, I would expect that by generating less output, the following operators will also generate or process less data. There's a couple of exceptions. Can anyone think of an exception to that rule? Can you think of any SQL operations where the output size actually increases if one of the inputs decreases in size? Okay, so here you're thinking about, like, if we decrease the number of entries in the where clause, then we might filter less and then the output size increases. Okay, that is correct. Okay, that's a good point. And that would be a reduction of the query. So if we drop operations. Okay, very good. And if you think about a case where the data basically decreases on one input and then the output increases, what kind of operations might we be talking about? Filtering is a good direction, yes. Anyone has any suggestions? If you think about, okay, self joins, might depend. So I mean, if the input to the join decreases, then often the join result also decreases. If you think about the set operations that we have seen, okay, I mean, for a union, if one of the inputs increases in size, then probably the output won't decrease either. It's the same for an intersection. If we think of other set operations, is there maybe something that comes to mind? In a way, yes. Yes, okay, very good. Here, there's the keyword. Yes, very good. So if we look at the set difference, basically you have one set and then you're taking out elements from a second set. Then if that second set decreases in size, then the total output of the operation actually increases. So that is one example where decreasing the size of one of the inputs might actually increase the size of the output. And in this system, the authors, they pay attention to those kinds of effects and will be considerate about where they reduce the size of the synopsis, because in some cases it might actually increase the size of the data processed by follow-up operations. All right, so now we have discussed this first stream data management system from already around 2003. It's a pretty classical system, but it has introduced a lot of the important concepts in the context of stream data management. This is why we have discussed it in a little bit more detail. Is there any questions about this first system before we start discussing about the next one? All right, I believe there is no immediate questions. Then we are gonna discuss now about another system, a recent one called ksqlDB, which is a system for distributed stream processing. And often, if you deal with really large amounts of data or queries, then we probably want to do a distributed processing. So ksqlDB uses several components that it is based upon. So we're going to discuss about those components too. ksqlDB in particular is based on Apache Kafka. And first of all, we're going to discuss a little bit more about Kafka. So Kafka is a Java-based stream processing engine. Now, you have a data which is partitioned into different topics. Then producers can add records to specific topics and consumers can subscribe to specific topics. Then they will get updates for those topics. Kafka already supports certain simple stream processing operations with the Kafka Streams API for filtering, grouping, and so on. This is a pretty popular system. For instance, if you have already used Uber, then know that the passenger-driver matching is internally done via Kafka. So this is a popular system. It is a little bit more low level because it only supports simple operators. A ksqlDB, which we will discuss in more detail later, essentially adds an SQL interface on top of that. Those Kafka topics that I mentioned correspond essentially to an ordered, to a log that contains ordered records. Each record essentially corresponds to a key value pair. Producers can append to this log, so we don't go back and update or delete previous entries, but we just append entries to that log. And the consumers, they receive updates for the topics they subscribe to. There's a couple of different types of topics. Regular topics, they essentially delete tuples only if certain space or time constraints are met. So if you're running out of space, you have to delete the tuples, or if the tuples become stale after a certain timeout, you might also delete them because now they are not interesting anymore. So the compacted topics, which essentially mean that new tuples, they override the old entries for the same key. Each record has a key and a value. And if you have a new record that refers to a key for which you already have entries, then the new value overrides the old value. So this is how those topics are structured, and they are processed in a distributed manner. Each of those topics is divided into partitions and at the same time replicated across multiple servers, which as usual gives us a fault tolerance, because if one of the servers fails, then we can recover the corresponding partition from others. And it also allows us to scale to more consumers. And here, okay, that is actually a great question. The definition of the compacted topic, whether it doesn't mean that we can actually update a tuple as opposed to just appending to the topic. Yes, that is a very good point. In a way, it does, yes. So for the compacted topic, you can update the old values essentially by appending new tuples. Yes, that is a very good point. So when processing those partitions, then we always have one dedicated leader server, which accepts new updates for the corresponding partition, and it propagates those updates to the followers. This is an illustration for how that looks like. So here we have 3 servers, and we have 2 topics. The first topic with 2 partitions, the second topic with only 1 partition. For each of those partitions, a different server is the leader, so it accepts updates from outside, and it synchronizes, it forwards those updates to the other servers, which are storing the same replica of the same partition. So this is how distributed stream processing works in Kafka at a high level of abstraction. Now, in order to make this efficient, we have to deal with insertions at a very high frequency. At the same time, we still want to be reasonably good at reading data. So Kafka Streams uses an underlying component, it's called RocksDB, which is very highly optimized for fast writes and has still relatively good read performance. And the techniques that this component uses, they are nowadays quite popular in the context of stream data management, or in general, if you have a lot of inserts to deal with. So we're going to discuss about that in a little bit more detail. The key idea is that in order to make writes efficient, you ideally want to write sequentially. And if you remember, for instance, the session on hardware, storage hardware, we have seen that those storage devices often have a preference for writing out data sequentially as opposed to having many random writes which are widely distributed, for instance, on the hard disk, because, for instance, the hard disk has to move mechanical components in order to get to certain locations on the hard disk, and doing that takes quite some time. So we want to try to write sequentially. And updates, yes, that means in general that we insert new tuples. In this case, yes, updates in general could also mean that I go back and update or delete some prior tuples, but in this case, the updates consists of adding new tuples. And for compacted topics, that indeed means that the newly added tuples might essentially, the semantics is that the new value overrides the old value. Yes. Okay. So in order to make writes efficient, I want to write sequentially. And there's an easy way of doing that. So if I want to purely optimize for insertions, and I have some pages on hard disk, and I have a buffer in main memory. So if we add the records to that buffer in main memory, I could just write out the entire buffer whenever it is full, and then I write the entire buffer to hard disk. And now I fill it up again, and once it is full, I again flush it to hard disk and so on. So this process here is totally optimized for insertions. I'm sequentially writing data, so that is very efficient. On the other side, what happens if I ever want to look up values for one specific key, for instance? And if I just write out things in the order in which they arrive, it means that here, in order to find a specific key, in the worst case, I might have to read everything that I have written, and that is clearly very inefficient. So this system is entirely optimized for writing data, but it's not very good at reading data, because the data that I'm writing doesn't have any structure that makes it easier to find specific records that I'm looking for. On the other side, I could optimize for reads, and I'm not going to discuss that in too much detail because this is essentially what we have seen so far. You might remember the indexes that we have discussed about, for instance, the B+ tree, and those index structures, they are very helpful in order to find specific data quite efficiently. And typically, if I want to be efficient at reading data, then I can just maintain an index over the data. So whenever I insert new tuples to my data, I would also update that index. And that means that I'm very efficient at finding specific records via the index. But on the other side, whenever I insert a tuple, I also have to update that index. And since this index doesn't store the data in insertion order, it means that in order to update the index, I need to update at least one page, which essentially means that I'm getting quite inefficient at inserts, because each insert is associated with one random write. Does that make sense, the trade-off between the write-optimized and the read-optimized storage? Any questions on that? And perhaps one little clarification on the last question that I had about what it means if you say that the leader accepts updates. I should also say that in accepting those updates, depending on the configuration, it might also entail talking to the followers and making sure that they have received the updates, such that even in case of a failure, I have stored the data somewhere. So there's a couple of steps that accepting updates entails. And then after having done all of them, the leader tells the producer that now the update has been safely processed, so the producer doesn't need to resend it. All right. So now we have seen two possibilities of dealing with data insertions. If I want to optimize for write performance, I can just append data sequentially, but then it's pretty bad for reads. If I want to optimize for read performance, I might want to maintain an index data structure, but then insertions are pretty expensive. So in the following, I'm gonna discuss about a compromise between those two, a data structure, which is very good at writing data and not too bad at reading data either. It's the log structured merge tree. And this is the data structure used by Kafka streams. Now, a log-structured merge tree essentially divides the data into multiple levels. The uppermost levels are stored in main memory. The lower levels are stored on hard disk, and each level is associated with a size constraint. And the size of those levels increases from the uppermost level to the lower levels. And it doesn't increase arbitrarily, but the ratio of sizes between consecutive levels always remains the same. So for instance, we could say that the next level is always 2 times larger compared to the last level. The way in which we use those data structures is this. Whenever we insert data, we first insert it into the uppermost level. And then whenever one level exceeds its capacity, we take all the current content in that level and merge it into the next lower level. So those merging operations, they are relatively efficient because here I can write data sequentially, right? So I don't insert single tuples randomly, but I'm merging 2 large batches of tuples, and thereby I get a pretty efficient write throughput. So whenever one of those levels fills up, I'm merging the content into the next lower level. So in the following, I'm gonna illustrate this by a minimal example. So here we have one buffer in main memory, and we have 2 levels stored on a hard disk. The first one with a size limit of 3, the second one with a size limit of 9. So here the size ratio between consecutive levels is 3. And here, as you see, currently those levels, they are not filled up. So there's still a little bit of space until we reach the associated size limit. For instance, for the middle level, we have currently 1 page stored within it. The size limit would be 3 pages, so we still have we have space for 2 more pages before the level becomes full. So now let's assume that we keep inserting data. So if we insert data, we always insert it first at the uppermost level. So now we insert the records, multiple records, until the buffer becomes full here. And at that point, we merge its content into the next lower level. So we essentially take the sorted content of the middle level and we merge it together with the content of the buffer. And that gives me 2 pages with sorted data, which now contain the tuples that previously were already stored in that level, together with the tuples that previously were stored in the buffer. So now here, this level contains 2 sorted pages of data. There's a question about whether we are keeping the level sorted globally or just within each page. And the answer is that we keep each level sorted globally. So there's a couple of different strategies, but for the strategy that I'm discussing here, we are maintaining 1 globally sorted order for the same level. And that makes it quite efficient to identify specific data that you're looking for within 1 level. And the question is how we can do a sequential write if we maintain a global sort order. Well, I mean, if you think back to the sort merge join, for instance, or generally to external merge sort, in those cases we always merge together 2 sorted runs of data, right? And that means that we always can completely fill up 1 page in memory with the lowest entries from both sorted input runs. And then once that page in memory fills up, we write it down to hard disk again. So this is the same principle as for the merging that we have seen previously. We don't need to work with single tuples, but we can fill up one entire page in main memory with the next entries in sort order taken from the two sorted inputs, and then we can write this entire page from main memory to hard disk. And this is how we get sequential writes. No, we don't. So the advantage of sorting, of merging two sorted inputs is that I know that in order to get the smallest entries from those two inputs, I don't need to load all of their pages, but I only need to load the next page with unprocessed entries. And this is why we absolutely need that the two inputs that we are merging together are already sorted. Because of that property, I only need to look at the next page from each input instead of looking at all pages, right? So this is why we did the external merge sort in the way we did it. We kept generating sorted ones that were larger and larger, but even though we had to write data multiple times, the advantage was that when merging things, we always could rely on the fact that our inputs are already sorted, and because of that, the merging is relatively efficient. All right, very good questions, very good questions. So basically, we have a process by which we can quite efficiently merge two sorted inputs and produce a sorted output again. And this process is applied in order to merge here the content of the in-memory buffer and the content of this middle level. And the output of that is a sorted sequence that contains 2 pages and combines the content of the buffer with the content of the middle level. So after the merge, now we have 2 pages at the middle level, which is still below the capacity. Now we might insert new tuples into the buffer until it fills up again. And now we merge that with the content of the middle level. And again, once we do this, we get one more page. All of those 3 pages contain sorted tuples. And now the level has filled up. I mean, there's still, we are not above the capacity. So here, I assume in this implementation, we can still generate new tuples and insert them into the buffer. And at this point, we are running out of space in the middle level. So now we have to merge things into the next lower level. So now here, I'm emptying the level 3, and instead I'm sorting and merging everything into the lowest level. So this is the way it works. I'm relying on those merge operations which avoid random accesses, which they can do because their inputs are also sorted. And I always merge things into the next level until the level fills up, and then I merge things into even lower levels. So over its lifetime, one of the tuples might first essentially originate in the buffer in main memory. Then at some point it gets merged into level 1. It might get merged there multiple times. And finally, it gets merged into the lowest possible level. So here, each tuple will be written perhaps a couple of times, but not too often. Now, if I'm comparing the complexity, the cost for insertions between those different methods that we have seen, for instance, if we consider append-only insertions, like the first method that we considered, if I measure the insertion cost by the number of page accesses, by the number of pages that I have written, then the insertion cost per tuple is essentially 1 divided by the number of entries per page, because I just insert tuples into a buffer in main memory, and I write that memory buffer to hard disk whenever it becomes completely full. So I only need to do this every once in a while, whenever my current buffer page fills up, this is why I'm dividing by the number of entries that I can fit on one of those pages. If I consider the way of using an index in order to allow efficient reads, but I have to update that index at each insert. In that case, I would typically expect the one page write, and that's still optimistic, per tuple inserted. So that is significantly less efficient compared to the first possibility. The log structured merge tree is somewhere in between. So here I have like multiple factors that I'm multiplying. First of all, I have the size ratio in there. And if you remember in the example that we have seen in this middle level, we actually merged things multiple times with that middle level. And the number of merge operations per level is essentially bounded by the size ratio between the different levels. So in the previous example, those levels could be, the size ratio would be 3. So that means I might merge things into one given level in O of 3 times. And we have also seen that the same tuple might start its journey in one of the top levels, but then it might descend more and more into lower levels. So perhaps I don't have to merge a tuple only on one level, but I have to merge it on multiple tuples levels. That's why I'm multiplying by the number of levels. But at least I'm not, I'm avoiding random accesses. I'm writing data sequentially during those merge operations. This is why I can again divide by the number of entries per page. So altogether, this gives me somewhat a compromise between the two previous approaches, which still has pretty good insertion performance. Now, when I want to read data from one of those trees, I mentioned that the data at the same level is globally sorted, which means that it is relatively efficient to find the correct data for a given key at a level. I might also have additional data structures that help me to identify the data I'm looking for in one specific level quite efficiently. For instance, I can use Bloom filters, which often can allow me to skip levels at which the data I'm looking for is not located. And Bloom filters is also something that we have quickly seen in the context of distributed joint processing. It is essentially a hash table which contains bits for specific hash buckets that tell you whether corresponding entries are in your data set or not. So since multiple entries map to the same hash bucket, it means that if you have a 1 at one of those hash buckets, that may refer to the data you're looking for. It may also refer to different data, so you cannot be sure, and you need to check in order to see. If the bit is set to 0, it means that the data you're looking for is definitely not located there. So you can often skip looking at specific levels. If you use a Bloom filters using the key that you're looking for as hash key. All right, so there's a couple of tricks that can play in order to avoid looking at specific levels or finding data at specific levels faster, but really just the fact that my data is sorted at the different levels, it makes it significantly more efficient to find data I'm looking for compared to having just one unordered sequence of data where I might have to read everything. So if I look at the reading performance, then if I do the append only strategy, the first one we have seen, in order to find something, I might have to read everything, which has terrible performance, of course. If I use the index, I am very efficient. I just look up things in the index and then I find what I'm looking for. The log structured merge tree again is somewhere in between. Pessimistically, I could assume that I might actually have to check every level, which is actually not realistic, but or to be very pessimistic, we can assume it. So we multiply by the number of levels, and then we would have one lookup at each of those levels. But altogether, this data structure realizes a pretty good compromise between insertion and reading performance. So that was one component of a ksqlDB. The next time we're going to discuss the actual interface, and then we're also going to see a little demo. Have a nice day, and then I see you again on Wednesday.